หัวข้อแรกของวันนี้นะคะเราจะมาดูหัวข้อที่ชื่อว่า Additive Manufacturing Print it light and right ค่ะ
Good morning, all of you. My name is Rajagopalan, Varadarajan. I work for MSc Software and I'm based out of Singapore. Thank you for giving me this nice opportunity for Sigma. And my presentation today is additive manufacturing, 3D printed light and right. So, Hexagon, MSc Software is part of Hexagon. We are a big global company, more than 4 billion euro company. What we are focused on autonomy. We are focused on innovation. We have more than 4,000 employees with R&D, 4,000 employees in R&D, and more than 3,700 active patents. And we are driven by purpose, that is efficiency, productivity, and quality. And we are proven consistently. We have grown big thanks to all our customers. From 500 million euro to today to 3.9 billion euro company with more than 21,000 employees across 50 countries. What is autonomy? Autonomy is something like this. About 200 years back, everything started as industrialization, mechanization, where the cars started, rolling out in the factory. Then today, automation comes in, where you can see that every factory you can see that there are robots, okay, for manufacturing and also for measurements, and everything is done automated. But what is autonomy is today, after with the internet, IoT 4.0, everything, we have so much of data. And how do we repurpose this automation with intelligent manufacturing? That is called autonomy, and this is where Hexagon and MSc is all about. So the road to autonomy, Hexagon as a company, we have both physical and virtual. Physical solution means, we have all the sensor solutions. Today, Hexagon has got the world leading the measurement solutions. For example, Leica camera is so famous in the world. It's a part of the Hexagon business unit. So we have all the sensor solutions where we can measure and we can inspect the data. And then we have the software solution that includes MSc. And we have what is known as fusion, okay, with the physical and also virtual. How do we fusion together to create the autonomous solution? This is where we work on. Today, 95% of all cars produced has Hexagon technology inbuilt. 75% of all smartphones, whatever the consumer electronics, whether you use refrigerator or mobile phone, and all the 90% of all aircrafts produced or 80% of orthopedic implants, this is on the medical side, has got Hexagon component involved. And we help our customers shape the future of products and services in all industries. So this is where Hexagon helps in globally. Yesterday, you have seen in Sigma's presentation on various technology MSc is bringing in, and so we are part of Hexagon portfolio, which is MSc Software. There are many different business units, and yesterday and today also you will see that which will be on the CAE solutions from MSc Software. So this is what we call as a design and engineering, all the way from structural analysis, multi-body dynamic analysis, thermal fluid, acoustic simulation, materials modeling. There are many different types of simulation solution Hexagon MSc Software brings on to all our customers. Today, I'm going to talk about the additive manufacturing, which is part of our manufacturing process simulation. So this is from the top one is all from MSc Software, and below that we have the entire CAM solution, which is all the way from the different types of CAM solution, okay, whether it's a 1-axis, 2-axis, 3-axis, or more than 5-axis machining, and also includes the reverse engineering. So all of them we have a part of our solution portfolio. Apart from that, we have the metrology, okay, which is including inspection equipment and also the quality measurement software. Today, Hexagon is in a position to bring all the CAD, CAE, CAM, and also the quality solutions all under one portfolio. In the industry today, you have CAD software, you have CAM software, you have CAE software, but today Hexagon, along with MSC, we are in a position to provide total solution all the way from CAD as designed, as manufactured, as optimized using simulation, and also as inspected. Okay, all of them under one single, from single offering from Hexagon along with MSC software. So this is the entire solution we providing. And last 2 days we have been talking on the design and engineering side. When it comes to, let me go to the additive manufacturing. When it goes to additive manufacturing or 3D printing, there are many challenges. Okay, many people know what is additive manufacturing is. One way is to do a traditional machining process. The other one is using 3D printing approach to produce parts. Okay, that is called the additive manufacturing. So in this additive manufacturing, there are different challenges involved. One is the 3D printed parts can be produced as a plastic or polymer, or 3D printed parts can be produced as metal. So the 3D printing of plastic is different, metal is different technologies. And also after when you do the 3D printing, it can be plastic powder or it can be metal powder. So the metal powder, the quality of the metal powder also has got a big difference. During the 3D printing process, the parts can fail, or after it also has got support structures. So when you remove the support structures, the parts can deform. Okay, the 3D printed part looks shape-wise okay, but inside there can be gaps or the voids that can also create all sorts of problems. So there are many challenges related to additive manufacturing. But now in my presentation today, how Hexagon along with MSC software, we are in a position to address different challenges in the 3D printing process. So in the additive manufacturing or 3D printing process, these are all the 4 steps. First step is a design and engineering. Okay, in this process, first is you optimize the design. Okay, because the 3D printing, when it is a 3D printed part, especially in the metal, it takes long time to print, and also the moment you can optimize it, okay, optimize the topology optimization, the 3D printed parts can be faster. At the same time, it can still have the enough strength for it. So this is the design and engineering side. Then the second one is the manufacturing. After you do the manufacturing, after you do the 3D printer, after you design, optimize it, and also you set up the 3D metal, 3D plastic, the process, 3D printing process, this has to be taken to a machine to print it. Okay, so in this process, this is the manufacturing process. One is to create the post processing, that is from the file created out of the simulation to manufacturable part at the 3D printer. And after that, you still need to do some cleaning. Okay, for example, removing the support structure. Maybe you want to put an additional hole or do some machining process. So this is the second step of manufacturing. The third step is a quality inspection. So you do the inspection. Okay, actually the part, is it the way it is printed? Is it correct? Is it the final deform? Do we have any deformed shape? Has got a more deformed so that it cannot be used. So this is where you do the inspection. The last one is the service life. After you do the 3D printed part, now you are going to print this 3D printed part on a manufacture in actual usage. Question is, does it have the stress? Does it can it service longer life? For example, in today's many of the applications involved in 3D printed parts is like you have a serviced part and it has failed, and now you want to have a replacement of the part which has failed. Now one way is to go to source part and again you get it done. But suppose if that particular part is not available in the market to buy, so what you do is you do a 3D print it and also put it into the actual condition. Now the question is, will that service long? Will this be in a position to take care of the service loads? Can it live longer? Can it service longer? Okay. So these are all the things. This is called the service life. So there are 4 steps all the way from design, manufacture it, inspect it, and service life. There are 4 steps involved in this additive manufacturing workflow. Example, look at this particular part. Okay, this one is an innovative part by a leading automotive German company. Okay, this particular part is actually sitting inside a bonnet of a car. So usually when you look at in a car, you have the airbags, okay, just to protect the driver in case of an accident. What about the what about the person who is involved in an accident? So this particular part sits inside the bonnet, and it can still use it when you open up the bonnet and close it. But at the same time, in case of an accident, what will happen is this particular part will fail. Usually, this is the bonnet, or inside the bonnet clamping arrangement. It has got multiple parts. Now we are going to replace it with the 3D printed part. It has got 2 purposes. One is a service as it is in service life, and the second one is in case of an accident, this particular part will fail, so that when it hits onto somebody, that particular passenger is still survivable. Okay, this is one thing. Second thing is, you can look at this particular one. This is an aircraft part which has got a complicated one, including the honeycomb structures. Okay, this is a metal part. So all these things are, complicated one. But how do we get acceptance of production of additive manufacturing parts for critical applications? What are the requirements? Number 1 is excellence in every stage and connecting different silos. It means that different processes we are able to connect it. The third one is solution is agnostic and easy to use. So when it comes to additive manufacturing, there are so many steps, okay, which I told you there are 4 steps involved. This is the 4 steps broken into individual components. There are 4 steps involved, okay. So there are multiple steps, and this middle one is a production management process, okay, where we are in a position to collaborate with partners to assist this. And there are many solutions built here. There are many solutions which we are able to provide to our customers in order to make this happen. And connect with others. Okay, so I'm going to explain about a case study, additive manufacturing driven lightweight design of a gripper of a packaging machine. So what does it do? Okay, so this is the original design. This is in this one, this is a gripper. Okay, basically this comes down and grips a part and going to take it to another place. So this is the gripper, and you can notice that there are so many parts. Okay, this has got sub assemblies and assemblies, and it is it's about nearly about 300 different parts are there. So this is our original design, and for assuming that this particular design we want to replace it with a 3D printer. Okay, and in this 3D printer we want to study with 2 options. One with plastic, the other one with the metal. So what we are going to do? The first step involved is we optimize it. Okay, basically using regular optimization. Okay, there are many classic legacy 3D topology optimization software available in the market, but this is what so we use one step. Okay, we try to do one step. Okay, let's try something else. So but this is optimized, this is able to do it, but the thing is it is not stiff enough. It means that when I grip it, I won't have enough enough hold so that I'll be in a position to take it and put it onto another place. So it is not really stiff. Now we have the solution. We have this something called Apex Generative Design. So using Apex Generative Design software from MSc, we are in a position to optimize this. Okay, so this is where we started, and we are in a position to create the same part, but the thing is it is 3D printable, optimize it. Okay, at the same time replace 300 parts by just one single part. Next is additional struts. Okay, so we look at it. Okay, but we still want some additional struts here. So we added additional struts. This again goes for a second round of topology optimization to make, because there is a customer requirement that they want to have additional strut here, maybe for some purpose of, the serviceability. Then what will happen is we use this particular topology optimization to start with, and we finally end up with a new design in which we are able to fulfill our customer requirement of additional struts, but still able to get to a part which is optimized. Then finally, we also try with another one, okay, in which for a serviceability point of view, the customer says, I want to have I want to make this not in one, but I want to make it in two, just for assembly purposes. So we do small changes here to make it into two. So this is a gripper study. So we start from here, we end up here. But in this process, what are the different processes in the additive manufacturing side? So this is what it is, okay? So we start with this, and you see that the original design with a 3 metal, 300 plus parts, it's about 870 grams. Okay, first polymer variant is 150, second polymer variant is 160 after putting the struts there and also making it into two, okay, based on customer requirement. So you can see that 870 grams changed to 160 grams, and at the same time, you see that, we also did one more design in which aluminum, okay, one is a polymer, the other one is aluminum, so 874 grams. Okay, so let's look into the steps. Okay, so this is the step. This is what we want to do, and this is the original gripper design. So in order to, this is what in the generative design process. Okay, this is what we are going to do, the topology optimization. What we are doing is we are selecting those places which we really don't want to change. Then you can see that in order to do that, to create the topology optimization, what we have done is so far is we said, okay, these are all the places we don't want. These are all the places where the gripper machine is going to work. Okay, these are all the places we don't want to change it. Okay, where when we do the topology optimization, we want software not to touch these parts. Okay, and we start with an approximate shape. You can see that, okay, it can be any shape, just an approximate shape, and tell the software, go ahead. And you can see that, okay, this is the original shape, and these are all the places. And we also put, something called like a support condition, because this gripper, it's going to grip and take it. So we put all the forces there. And you can see that on the left, you can see how the software looks like. This is what we call as a generative Apex software, full screen. And then we tell the software topology optimize it. So you can see that it goes through different iterations, start with some approximate shape, and depending upon the loading and also depending upon the material and where we are going to support it, and gives you a shape. Okay, so this is the shape, and tells you 56 grams saving, 56% of saving, okay, happens. And this is the part after topology optimization. But that's not good enough. Okay, after we create the topology optimization, we want the software to create a NURBS geometry. Okay, so this is the NURBS geometry. Okay, this the original part. Okay, you can see that the one which is now what you are seeing is a NURBS geometry. It means that it has got all the surfaces, everything there. Okay, then we take it to Nastran. MSc Nastran is a world famous software for structural analysis, dynamic analysis, and use Nastran to check, okay, is this this gripper has got the deflection and also the stresses are okay while in operation. So we do all the support conditions and also loading conditions, and we check quickly. So we started with the topology optimization, then we go through Nastran, and we also do this. Then we go through DGMAT additive manufacturing. This is where we are going to test it on a 3D polymer printing process. Okay, so this is where the 3D DGMAT is the world famous software for materials. Okay, in this one we use the 3D polymer printing process, and you can see that in the screen what you are seeing is as the 3D printing process happens in the machine, how really it comes up. And the red color, all those things tells you the color difference as far as deformation. Now from plastic we want to put it onto metal. Okay, in this metal, you can see that we replace the polymer with aluminum and use our Simufact Additive Manufacturing software to print this process. After we have printed, then we are going to take it to machine. Okay, so when you do the machine, it is now from the machine you are going to do. See, now this is the Simufact Additive Manufacturing process. This is for the metal, and you can see in the screen how when the 3D metal process works in the machine, how the build process basically slice by slice. Okay, this is how it is done. The color here, it tells you the maximum deformation. Okay, the maximum deformation, and also the red color shows the maximum deformation. On the screen, you can see that the color shows. Now, when it comes to 3D metal printing, now the technology has evolved. You don't need to print one by one. You can see that two parts simultaneously printed, and you can see that the maximum deformation and the surface deformation shows higher. And what we do is something called compensation. Instead of printing like this, we print with a negative deformation. Then we do this printing. So then it goes through. This is the printing process. Goes through the printing process, and we see that this is how after doing the compensation, the part is okay. Then it goes to the next step. Then we do the eSprint is a part of Hexagon software, which does the post processing. What you saw so far is the simulation process. Now we are taking this to a machine. Okay, and this is what we call as a digital twin. How you see actual part, how this whole thing will be, and the actual part. Then it goes through the additional one, okay, in which you want to do the CAM process. Okay, so this is how the whole thing CAM process. This is the CAM process. We are in a position to do that. And finally, this is the metal geometry, and you can see where we started from actual gripper, and we finally ended up on this. Okay, so this is the complete end-to-end process Hexagon MSC software is in a position to do it. Next one is on the screen. What I showed you on the screen as a part of the screen capture on the software, you can see that additive manufacturing for polymers. You can see that, okay, this is how it is. And during the polymer printing process, okay, you can say based on the orientation, this part can be manufacturable or not manufacturable. This part can be manufactured, all those things. So you can check for warpage, residual stresses, temperature, all those things you can check for polymers. And not only that, during the polymer printing process, okay, there are two types of printing process, as I mentioned. One is a polymer, the other one is a metal. So when it comes to polymer printing process, you can orient the part in many multiple ways. Okay, the purpose is why you orient it multiple ways, because you want it printed faster, at the same time consume less metal, and also consume less number of support. So during this various printing angle, okay, this is the printing angle. You can see that, okay, at some point, it says these are all things okay. How much the pressure, okay, but also you see here a kink. It shows that at particular printing angle, this is a printing, okay. The way you print, you orient this in the 3D printer. You can see that at this particular from here 60 degrees to 80 degrees is not okay. Okay, why it is not okay? Because this will become, a kind of a bulge. Okay, this particular part, if you print it at this angle, is not okay because you will have a shape like this. But otherwise, rest of them are okay. So you can say even before you do the 3D printing of polymers, you can check, okay, is this finally printed is okay or not. Then finally, okay, so we started with topology optimization. We did a build process. We verified for polymers. We tested for metal. But after that, after you have done, then you want to inspect it. Okay, inspect means you take the part, okay, and you want to do check. Okay, one is a physical dimensions of outer shape, the second one is inside of it. So today Hexagon today provides various types of inspection equipments. Okay, in this one you can see one is a physical equipment. These are all the scanners. Okay, it can be touch probes, it can be scanners, and we also have got powder inspection. Okay, for example, physical measurements are a thing, okay, but during the printing process, whether it is a polymer or metal, we are in a position to check at a sub-micron level. Okay, you can see that you can imagine powder itself is so small, okay, so tiny, but we can inspect it by scanning it and looking at how at the powder level. Okay, actually it is just one single grain of metal, but you can also see that within this red color shows the inclusion. Okay, when you have a metal, that can also powder, it also has got inclusion, so we can check at that level. So different scanning equipment, it can be physical measurement, touch probes, or it can also have a scanner, as a digital scanner, and also can also do a CT scan to test at the powder level. So all of them are possible. So this is the part scanning. Then you can check for 3D model to scan. Okay, so when you do a scanning, it's something like a human. If we have an issue, we go through a CT scan, and the same thing, a part 3D printed part can be CT scanned, and within the CT scan you can check whether outside on the surface, but also you can check inside of it. Okay, how much is the gap is there? Okay, is there any porosity is there? Is it will it cause any issue during the service life? And finally we do the functional test. Okay, so different software from MSA software, test for structural analysis, CFD analysis, acoustic analysis, and all those things. So we also brought one more thing, what we call as a Simufact Additive Machining. Okay, this is a totally new module from MSc today, which is unique in the whole world. What does it do? After you do machining, you have a 3D printed part, and after you have done a machining, that is going to change the stress and deformation pattern. Okay, and you want to put it into a service condition. Okay, it can be a life prediction, it can be just dynamic condition. So we are in a position to take results from 3D printed part post machining into the service condition. So all these different technologies put together, this is what we call as a Simufact Additive Machining software. Okay, so we brought this. Finally, one example, which I like it to explain. So here we have this example. So I just now I talked about the entire manufacturing process, end to end. So here we are going to explain about one case in which we have one example, very interesting example today. In the world today, people are going for replacement parts. It can be joint, or this is an example of a person involved in an accident, and requires a hip replacement, a portion of the hip replacement. So far I explained about a gripper example in which we started with the basic design, and we had an approximate shape to come with the final design. But in this situation, it's a different situation in which a person is involved in an accident, and now we want to CT scan that particular person, and using a scanned part to create a 3D additive manufacturing part as an implant. Okay, so this is where we start. Okay, so again, this whole process from MRI to application, fitment on this. So this is done locally here within this region. Okay, so this is how it is, and different software used. So VG, the volume graphics, is a Hexagon software, and here we are going to do a CT scan. So this is the person involved in an accident, and is going to go through a scan, and this is a CT scan. Like a metal, so CT scan, and going through the CT scan. From the CT scanned image, we are in a position to recreate a 3D CAD model. You can see that this is a 3D CAD model scanned from the scan, creating a 3D model, and use that 3D model to use DG mat and do a 3D polymer printing. And what you see here is the computer in which the 3D plastic part is being produced. And what you see on the screen is actual manufacturing process. Okay, yes, layer by layer, the whole thing is being printed. Okay, this is how it is. The printed part goes through step by step, and finally the part is printed, and we use hexagon technology to scan it. Now, from 3D scan, we created a 3D part, and from then use the scanner to look at get the cloud of point and recreate the geometry again and put it into the human body, how really this is going to fit. From you can see that in this, what is beauty in this one is this particular portion. This one is from a CT scan, and this one is from the cloud point of data, recreated a CAD model, putting into the actual human body. Okay, will this fit post processed? And so far you can see that that's what is the 3D printed light and write.